as a kid, um, I believed in magic. Like I'm so addicted with Naruto. Like how they were able to make and control their chakras and their energy points. So I think the magicians and the wizards of our times right now are those who can understand data. Now, data is very powerful in our context right now because you can read the mind of people if you know their data, right? So hackers can hack into Facebook accounts, or even Cambridge Analytica can scrape your data and tell you that these are your personality type, these are your religious views, political views, and so on, right? So you can also use data when you have a time series to predict things. So you can do some like alternative to tarot card readings. You can use data to do forecasting and finding patterns, no, to predict future events. So I think the data scientist or any job related to data is really similar to doing sorcery or magic, because the things that magicians do, the things that wizards do, I think data person or data solutions person can also do as well. Okay, so enough with the pep talk. This is the outline that we have for today. I will just introduce you some of the concepts and the topics that we use for statistical data science. No, so we will try to use some common libraries that I have already discussed before, like pandas, numpy, and scipy.stats. At the end, I will also provide you some resources if you want to extend your studies. So we only have 1 hour, so it's hard for me to compress as well. Uh, a lot of things that you should learn about statistics, but I know most of the audience here had some statistical lessons already from their high school, from their university. So I think this is a bit of a review, okay? So when we talk of statistics, we talk a lot about data. So I really believe that statisticians are the OG data scientists, right? But they had to evolve. The onset of big data, the onset of fast computing capabilities in our computers, the smaller number of resistors and transistors that we can pack to our computers resulted to a new kind of field. Now, statisticians, mathematicians are obliged to learn programming, are obliged to learn business skills, are obliged to learn how to analyze and crunch big data. So that is why I think being knowledgeable in statistics is very important if you want to be a data scientist, because most of the pipeline, most of the workflow that we use in data science, even in machine learning, we use a lot of concepts in statistics, in linear algebra, in graph theory. So having knowledge in statistics and mathematics is really an important tool. So there are different types of statistical analysis when you're presented with data, right? I think most of you are familiar with some of this already. So the first one is descriptive, okay? From the word itself, it just describes your data. So um, what do I mean when I want to statistically describe my data? I want to look at my measures of central tendency. So getting the average, average or mean, getting the median, getting the mode, getting uh, the measures of variation. So those kinds of things. So in inferential statistics, on the other hand, uh, sometimes we want to infer something that's not explicit to our data, right? So for example, if you remember your hypothesis testing, right? Sometimes you can't analyze the whole population because it's too big. So you just get a sample of that data set and you want to make assumptions uh, to the population just basing on that sample data set. So that's inferential statistics. You might also want to look at differences in populations, in means of populations, right? You can, if you remember some advanced statistics that you use, right? Like the t-test uh, and ANOVA, z-test, those kinds of things. And also use uh, statistics to do analysis on associative items. So for example, if you're presented with a data that is in a table and that table contains a lot of columns, you can do associative statistical analysis by comparing the values of one column to another column. So If you can recall some of the terms like covariance, like correlation, so those are the things that we use to associate variables with each other. So some advanced tools that data scientists uses um, borrowed from linear algebra, like singular value decomposition, dimensionality reduction from principal component analysis. I think these are all buzzwords, but if you enroll yourself to Coursera, if you enroll yourself to online courses in Udemy, you will definitely come across these terms. Okay, and there's a reason why these terms are always present to those conversations, because they are really important in the pipeline of data scientists. So understanding those terms are very important if you want to have a career in data science. So when my friends ask me, hey, Bash, hey, Albert, so what's your work? So I just say, I work in computing. So that's what I do. Okay, we now live in a world of data, and data is knowledge. Data is power, right? So if you can do anything with data, um, you can do a lot of things. Okay. So the last item that we have here is predictive statistical analysis. So um, other buzzwords that they use would be regressions. So if you want to predict future values based from historical data, if it has a linear trend, if it has a linear pattern, then you use regression. You can also do multiple linear regressions if your data set is more complex. What other predictive tools that we use in statistical analysis would include other advanced things like ARIMA, so moving averages, autoregressive, moving averages, and the ARIMA family. So those are the things that we normally use in making sense of data around the world. So for example, if you plan to work in financial or studying stock markets, no, um, normally uh, forecasting is very important in analyzing stock data, right? So given a time series, you would want to have a certain confidence level of how the market is will be doing in certain span of time. So that's some of the use cases that we have for doing predictive analytics. Okay? Um, I was not able to mention here, but some interesting application of statistics as well would be on outlier analysis and outlier detection. So later on, I will give you some concepts of how we define outliers, um, and why is it important to consider, because some industries or some jobs in the industry are very reliant to understanding these outliers like risk management, right? Risk reduction. So they want to look at the data, they want to look at patterns and think of anomalies in their data set, because those are their particular field of interest. So if you look at job posts concerning risk management, then if you want to look at posts of risk management, then you're technically doing data science, because the tool set that is included to those job descriptions are really the arsenal skill sets of a data scientist. Okay, so I need to do some demonstration. Screen to share a new screen. But I don't know where is that screen. Share. Okay. So hope you can see my screen. So let's consider a test example. If, for example, we are given a data set. Let's say we're given age data set of Filipinos, for example. So generally, if you look at the age of the people in the Philippines, you will see that you will find a certain pattern, right? Like if you list down all of the ages, 1, 2, 3, 4, until 101, for example, you will see that there are varying frequencies of these ages, okay? So if I plot it in an axis, and the x-axis would be the age, and the y-axis would be the frequency. You will see some pattern, okay? Um, statisticians call this the normal distribution. And this type of distribution is very, very, very common in nature. So my background is physics. So my motivation in studying physics, aside from wanting to become a magician, because in physics we studied plasma physics. Um, so we studied like glowing air or something. So it's very interesting that most of the patterns that we see in nature can be described by mathematics, can be described by statistics. For example, rain. If you look at the distribution of rain, you will see that generally it is raining harder at some places at a particular time, and some areas would have only drizzles, for example. So if you plot the distribution of rain, you plot the distribution of rain, you will see that it will be like biased towards some degree. So when natural scientists look at that phenomenon, they speculated, oh, this follows a certain mathematical formula, and they call it the Poisson distribution. Okay. So what else? Even Newton, even the postulates given by Newton, right? If you have two stars that are, or two planetary objects that are separated at a distance, you will always see that the relation of these two planets are 1 over squared, 1 over r squared. It's always inversely proportional to the distance squared. Same with the small atoms, right? If you look at the separation of the charges of elementary particles, for example, you will see that it's always 1 over r squared. So understanding the mathematics and the statistics behind these concepts is very important if you want to have an accurate description of our world. Okay, so how can this be applied to real world data sets? So for example, if you're working with Food Panda, this is not an advertisement. I just ordered my food in Food Panda, so, or Grab Food, for example. So if you look at their software, so once you order, there is a relative waiting time, right, before your order reach you. So if you look at the properties of the waiting time, you can actually plot it, and you will see that, oh, this variable is really dependent to time, and there is always a mathematical model that you can use to make sense of that. Okay,